Okay, so I'm going to be talking about the calculations that you need to do for the gas chromatography lab. And I've cheated a little bit and drawn up a chromatogram example. So for the GC lab, you're going to have data that looks something like this for both your solution B, your known standard, and your solution C, your unknown plus internal standard. So you have a methanol peak, which we really don't need to worry about for this experiment. And then you have an analyte peak, which I'm going to abbreviate by X, and an internal standard peak, which I'm going to abbreviate by internal standard, or IS. And you would only get a chromatogram that looked like this, where this was your analyte, if the analyte had a lower retention time, was earlier eluting than the internal standard. And remember that we're going to be looking at peak areas to measure the response, so that's the area under the curve, the shaded area, right? So the relationship we're going to use is a lot like the relationship we used for the ion chromatography lab, where we said that the area of the internal standard over the concentration of the internal standard is going to be equal to some factor times the area of the analyte over the concentration of the analyte. Okay? And for solution C, or sorry, solution B, we know the concentration of X and the concentration of the internal standard, concentration of the analyte and the concentration of the internal standard, because you made these from known materials, right? You added a mass that you recorded of your analyte, and you added a mass of the compound that you picked as your internal standard, and you know how much methanol you added. So you know the masses and you know the concentration in terms of mass percent. And you also measure the area of the internal, the area of the analyte and the area of the internal standard. So if we put all these values into this equation, you can see that what we're going to do is end up solving for F, right? Where F is equal to the area of the internal standard over the times the concentration of the analyte over the concentration of the internal standard over the area of the analyte. Okay. So this is going to give you a factor that you're going to use in the subsequent calculations. And the reason that we're using this internal standard method, or one of the reasons, is to demonstrate how the internal standard can be used to correct for issues of imprecision. For example, one obvious area of imprecision is the manual injection. So in this case, you can see that because the area of the internal standard is ratioed to the area of the analyte, if the area of the internal standard goes up because you're injecting more, then this is going to go up, and it's going to go up by the same amount, and so that's going to cancel out. So this factor is going to remain the same. And that's the real power of the internal standard. So in the next one, I'll talk about using this in for the solution C calculations.